Hi, welcome back to a new lecture from Computer Vision from Scratch. Today, we'll be looking at Inception V1, also popularly known as GoogleNet. This is a convolutional neural network architecture which is very famous. It won the first place in the ImageNet challenge in 2014, and the paper associated with this has achieved truly legendary status with 68,500 plus citations. This is a super famous architecture which we still use today. If you are a person who is working in computer vision, I'm 100% sure you have tried Inception V1, V2, V3, different models. And today we'll be spending some time on trying to understand what made GoogleNet so popular, what made it so effective, and how did it overcome some of the shortcomings that the previous architectures like AlexNet, VGG, etc. had. So if you are watching this lecture series for the first time in this video, but don't worry, like I'll be giving you a proper recap of what exactly are we doing, what exactly have we been doing so far in the lecture series, and then today exactly how are we going to construct the GoogleNet for performing a 5-class classification on the 5 flowers dataset that we have been using throughout this course. So with that, welcome to the lecture. In the previous lecture, we discussed about the VGG architecture, which tried to use very basic 3x3 convolution filters, unlike some of the previous architectures like AlexNet. But in general, what researchers working in computer vision, what they were trying to do was they were trying to build deeper and deeper convolutional neural networks. So in general, the machine learning community, especially the deep learning community involved in CV research, they wanted to build deeper and deeper CNNs because it was very clear by 2014 that depth means you can learn more features in complex images. So it was clearly understood by 2014 that if you want to perform multi-class classification on data set that is not really distinct, then you have to have depth. But the problem was, the more the depth was, it was harder to train the neural networks because simply there will be too many parameters. So if you want to update that many parameters, when you are back propagating, it's very difficult. There were challenges like when the depth is too much, the initial layers will experience vanishing gradient. So they will not get updated. The weights and biases in the initial layers will not get updated as fast as how the later layers experience the change. So these issues were existing, and there was also a huge computational expense. So this was the architecture that we discussed last class in the last lecture about VGG, where they simplified the whole idea. Instead of using convolution layers with different convolution filter sizes, you look at the convolution filter size here in VGG, it was all 3x3 filters. Of course, there were max pooling and other operations happening in these like in between these convolution layers. But what this showed is that you don't have to build CNN or convolution filters of varying sizes. All you need is pick this size and go for depth. So this was a very interesting finding. And for this reason, VGG paper, as we discussed in the last lecture, it had won the second place in 2014 ImageNet challenge. But then today we are discussing about GoogleNet, which won the first prize in the same challenge. And we'll discuss why GoogleNet was superior compared to VGG. We will also run it on our dataset and we'll compare the accuracy and the validation and training accuracy and see which one is better for our case. And of course, we'll be using transfer learning because we'll be using pre-trained neural network. We have learned in the course that starting the training from scratch is not at all easy. It's very difficult to train a neural network from scratch because our dataset is very limited, right? So the problem with VGGNet was the total number of parameters in the VGG architecture was about 138 million, which is a massive CNN architecture. So although it was simple 3x3 convolution filters, the total number of parameters were huge. So then the researchers at Google, which devised this idea of Inception. So it was initially called as GoogleNet, but then later it was renamed as Inception V1. V1, I guess, for version 1. There are Inception V2, V3, etc., which you can use if you want to train some of your data set. But basically, the question that they asked was, can we design an architecture that has depth, but also it's a bit efficient while training, right? So the answer to this question was GoogleNet, what they proposed in 2014, 2015. So the basic idea was, instead of just looking at 3x3 filters, they used multi-scale filters within each layer. I'll show you exactly what this means while showing you the architecture of Inception or GoogleNet. But basically, they realized that you don't have to just keep using 3x3 filters, unlike what VGG was doing. You can actually use filters of different sizes, and that is actually beneficial in reducing the number of parameters so that the total neural network architecture is not so huge. And this is one of the first authors. I mean, this is the first author of the paper, Christian Szegedy. I'm pretty sure I'm pronouncing the second name incorrectly, but this paper has now 68,500 plus citations. Please do check this. This is from his Christian's Google Scholar page. So before we moving ahead further, I want to give you a brief recap of what all we have been doing so far in this course. All right. So just to recap, we were using the 5 flowers dataset, which is a set of daisy, dandelion, roses, sunflowers, tulips. It's a set of 5 flowers, and there are approximately 1,000 images in each class. So the task here is a 5-class classification. And for this, we are trying to build step-by-step neural networks of increasing complexity. So at the very beginning of this course, we started with a linear model with no activation. So the structure was something like this. We had RGB images. So there are 3 channels, red, green, and blue. We converted that into a flattened layer, right? So this RGB will be this RGB, like that. So how many ever number of pixels are there total, that many number of nodes are there after flattening. And then we had a fully connected final output layer. So this had 5 nodes because we are performing a 5-class classification. This was fully connected. Every node in this layer was connected to every node in the final layer. The only place where we had an activation function. So this overall neural network architecture for linear case had no activation. The only case where we had activation was we had a softmax function at the very end for converting the output values into probability distribution. Then we saw that this linear model was actually not so good. It had 40 to 45% accuracy, which is not bad. We are performing 5-class classification. The worst model performs a random classification. It has 20% accuracy, right? So linear model is not so bad, but still it's not like 90-95%. And the loss was 10 to 20. This was the order of magnitude. Then what we did is we started looking at, okay, can we add hidden layers? Maybe that will make it better, and also add activation. So we added 128 node hidden layers as a new layer, right? So we flattened, then we add the hidden layer, and then we have the 5 node final output layer. And we use rectified linear unit, ReLU activation function. This surprisingly did not improve the accuracy. Accuracy was still 40 to 45%. And when I say accuracy here, I'm talking about training accuracy. Validation accuracy was even lesser. It was 35-40%. But the good thing was loss now decreased by almost an order of magnitude. It was 1 to 2 instead of 10 to 20. And the reason for this was the classification accuracy did not increase because the percentage of images that we were correctly classifying was pretty much the same. But the loss decreased. This is surprising. Like, how come loss decreases by an order of magnitude, but accuracy does not change? This happens because the model is now making more confident predictions. And because of that, the loss associated with every single prediction has decreased. So because the prediction, let's say you are supposed to predict 1, 0, and in one case you make the prediction like 0.6, 0.4. Here also, you are essentially saying you are looking at class 0, because if this is class 0 and this is class 1, and let's say this is the true label and this is the prediction. In this case also, because 0.6 is greater than 0.4, you are saying that this image is belonging to class 0. So prediction is correct, but it's less confident. Whereas if you make a prediction like this, it is more confident, right? If you make a prediction like this, then it's more confident and it's correct. So this is what was happening, but accuracy did not increase. Then we thought, okay, maybe we are performing overfitting because training accuracy was 40-45, validation accuracy was 35-40. So we thought, okay, how can we minimize overfitting? Then we decided, okay, we'll add regularization, batch normalization, dropout, and early stopping. So this allowed us to surprisingly increase the accuracy by to 50 to 60%. This was validation accuracy. We also noted that for some cases, training accuracy was reaching even up to 70-80%, close to 70%. So that was a good thing, but not the best thing. Why? Because still not as good as what we would like the training to be, because we are used to having multi-class classification accuracy of 95%, 99%, etc. So 50 to 60% is, of course, it's an improvement, but it's not good enough. Then we discussed, okay, this is why we should not be training completely from scratch. We have to use pre-trained neural network. So we introduced the concept of transfer learning, where we started with ResNet, although ResNet we will have an entire dedicated lecture later. We started transfer learning, where we used a pre-trained neural network, and then we trained the final classification layers alone. So we froze the previous layers, and the classification layer alone we trained on the 5 flowers image dataset, and we obtained actually 100% training accuracy and 80% validation accuracy. Significant improvement, but still, of course, there is some overfitting happening. So this was the case with ResNet, where we used transfer learning. Then we thought, okay, now let us start with the proper chronological order. The first neural network which completely revolutionized the way deep learning operated was AlexNet. It was introduced in 2012 by these 3 very famous people. Alex is the name. AlexNet is named after this first author, Alex. Then there is Professor Geoffrey Hinton. He won the Physics Nobel Prize in 2024. So he is also one of the authors of the paper. Then we have Ilya Sutskever. He was one of the co-founders of OpenAI. He is also part of the paper. And this paper is a truly legendary paper. It has 170,000 plus citations. So we implemented AlexNet that was pre-trained. Until this point, we were using TensorFlow Keras. But then for AlexNet, since we did not have pre-trained AlexNet in TensorFlow, we switched to PyTorch. So in AlexNet, we obtained 95% training accuracy and 90% validation accuracy. And this was the best. This truly made us happy for the very first time, because we have a model that is not overfitting, and we are getting very good training and validation accuracies. And of course, this could be improved by further hyperparameter tuning, hopefully, which we can do later. Then in the last lecture, we discussed VGG, where we were hoping to have better performance than AlexNet, because that was the whole idea behind VGG, right? When it was introduced in 2014, whereas AlexNet was introduced in 2012. VGG is supposed to perform better, but in our particular case, it did not perform much better. Validation accuracy was 85%, training accuracy was 75%. And one more thing to note here is we ran for 50 epochs, whereas until this point, we were only running for 10 epochs, right? So until this point, only 10 epochs, but here in VGG case, we had to switch to 50 epochs. But even with 50 epochs, validation accuracy only reached 85%. But the good thing to note here was, see, it's not overfitting, it's actually underfitting, because training accuracy is 75% only, but validation is 85%. After 50 epochs, we have a decent data set, like 1000 multiplied by 5, around 5000 data points are there. How does this happen? This happens because the pre-trained weights and biases of VGG are already very good. So which is why the validation accuracy is good and training accuracy is yet improving. So we can improve the training accuracy further, hopefully, if we run for maybe 200 epochs. But the reason why we did not do that was because even to execute this, it took maybe 3 to 4 hours of running the code. Whereas for the previous cases, it was a few minutes. So of course, we ran for more time. So it was a bit inefficient. And maybe this is also because VGG is a huge neural network architecture. So maybe to train even the final layers, the unfrozen final layers, it takes time. But in any case, we were kind of happy with the fact that we are not overfitting, because if this train and validation accuracy were flipped, we would not have been happy. But this made us kind of happy. But we were still a bit disappointed to see that VGG did not perform better than AlexNet. But we also discussed that VGG placed second in the ImageNet 2014 competition, but the first place winner was GoogleNet. So this is where we come to today's lecture, where we will be discussing about GoogleNet. But I hope the recap was useful to you. You understood what we have been doing so far in the course, so that you can catch up immediately with what the kind of model that we are discussing today, right? So before we enter into the lecture, just wanted to remind you, as I always do, starting a course or lecture series is the easiest thing to do. Many people do that. As you can see in this graph, the initial lectures almost always have a very high number of views, and only a fraction of people remain by the time the course reaches its end, the 35th lecture. So please remember that you have started this course with a reason. You want to become really good at computer vision. And so if you have started this, remember the reason why you started this, and let's take a pledge together that because we have started this with a serious, solid reason, we are going to complete this, right? So that is a pledge that we will all give to each other. If you want to keep yourself accountable, or if you have a friend or acquaintance with whom you are taking this course, keep mutually accountable for finishing the lectures. If you want to keep yourself publicly accountable, feel free to put a comment so that you are kind of giving yourself some kind of public accountability. But other than that, I hope all of you are doing good, and let's get into the lecture. So with this, let's get into Inception V1, aka GoogleNet. The Inception V1 or GoogleNet has something called as Inception Modules, and you have multiple of these modules stacked in series. But within each module, you perform a certain set of operations in parallel, where you have a fast 1x1 convolution layer, you have a 3x3 convolution filter, 5x5 convolution, then 3x3 max pooling, and then you also have a 1x1 convolution following this. So let me show you what I mean by this. So let's say this is the previous layer, 28x28x192 channels. Then you have in parallel a 1x1 convolution, 1x1 convolution, 1x1 convolution, max pool 3x3. Then following this 1x1, you have a 5x5 convolution. Following this, you have 3x3. Following this, you have 1x1. And finally, all of this is concatenated into the final output channel. This is one module of Inception. There are many such modules in series in the whole Inception architecture, which I will show you in the later part of today's lecture. But just look at these numbers, right? So the number of channels are getting added. So this is 28x28x64. This is 28x28x128. So you add 64 plus 128 plus 32 plus 32. So that is 64 plus 128 plus 64. This is 128 plus 128, which is 256. So when you are concatenating into the final channel, final output node, the sum of the channels 64 plus 128 plus 32 is matching this, right? So you can logically see where the channels are getting split and how it is getting concatenated. Now, if you would ask me, how did people come up with this kind of an architecture? I have no idea. I'm sure it's a lot of genius. I'm sure that there are a lot of genius people who work behind this module, but also there is a lot of trial and error. So, but surprisingly, this works. Unlike VGG, which just had 3x3 convolution layers, this is one module of Inception. And imagine stacking these modules one after the other in series. That is sort of what you should imagine when you hear about Inception or GoogleNet, right? What this approach allowed them to do is you could learn global features and local features because you have small convolutions happening. So small convolution mean you are focusing at feature at that particular or the neighborhood of those pixels. But 5x5 convolution will allow you to learn features that are a bit more spread out, right? Because there are 25 pixels that are under consideration at the same time. Whereas in 1x1 convolution, you're looking at one pixel. So overall, this kind of a module allowed the neural network to not just look at local features in the image, but also global features at the same time. Then this allowed the neural network to be deeper and wider. What do I mean by deeper? Deeper meaning you can put multiple of these modules in series. So that adds to the depth. And what does add to the width? Because you have these parallel operations, 1x1, 1x1, 1x1 max pooling. All of these are parallel operation happening at the same time. So that adds to the depth. And also it allows the model to learn local and global features. And then surprisingly, the total number of parameters in GoogleNet was much lesser. I'll show you exactly how much GoogleNet V1 had in comparison to VGG. As we discussed earlier, VGG had 138 million parameters, right? So let's also look at how this 1x1 convolution, for example, is beneficial for reducing the number of parameters. So let's also see that. So what exactly does this 1x1 convolution do? So this is the 1x1 convolution, right? Here. When you have 1x1 convolution, you are looking at one pixel. If this convolution filter is acting on an image, you are looking at one pixel at a time. Depending on your stride, you will be moving multiple pixels. And these 1x1 filters operate across channels. So for example, here we had 192 channels in the beginning. And then when you have a 1 by 1 convolution, you can define the number of output channels that you want, which will suppress the total number of parameters that you need. I'll show this to you with an example. So basically, you can reduce the input depth, meaning input number of channels, and later you can apply 3 by 3 or 5 by 5 convolutions on the compressed input. Why do we call it as compressed input after the 1 by 1 filter? Because in compressed input, you will have lesser number of parameters. So here is an example. If the input has 192 channels, and let's say it's a 5 by 5 image, so 5 by 5 by 192 channels, right? Then you will totally have 5 times 5 times 192, so which is 25 times 192, around 4,800 weights per filter. But let's say before we apply this 5 by 5 by 192, we pass the image through a 1 by 1 convolution filter. Then basically you will have 1 by 1 by 192, and so this is the total number of weights in the 1 by 1 convolution. But let's say we are passing the convolution filter such that it has 16 channels as the output. So here this 1 by 1 had 16 channels as the output, right? Here it had 96 channels. Here it had 192 channels. But similarly, when you use 16 channels, then you are compressing, instead of 5 by 5 by 192 number of weights, you will have 5 by 5 by 16 number of weights, which is 400. But in the 1 by 1 convolution, you have 192 weights, so you have to add 400 plus 192, which is total 592 weights parameters. This is almost 88-90% reduction compared to 4,800 weights per filter. So this is the huge advantage of having these 1 by 1 convolution layers or filters before you pass the resulting output into 3 by 3 or 5 by 5 filters. So overall, this is the structure. VGG16 had 138 million parameters. It had 92.7% top 5 accuracy in the 2014 competition, and that placed second. In GoogleNet, they had 93.3% accuracy, but with just 6.8 million parameters. Mainly this was because of 1 by 1 convolutions. Whereas VGG, they went with depth. They had just sequential layers, no wide like parallel filters, and they just used 3 by 3 convolution. Then later came models like Inception V1, which we are not discussing today, but they had slightly improved accuracy with intermediate number of parameters, right? So this is what Inception accomplished. But basically, just look at the number of parameters, 138 million. So this one had almost 131 million more number of parameters compared to Inception V1 or GoogleNet. So VGG, while it was a legendary architecture, and surprisingly that paper has more citations than the Inception paper, the architecture was gigantic and it had slightly lesser accuracy in the ImageNet competition. It doesn't mean that for all data sets, VGG will be better. Inception V1 will be better. There is nothing like that. It depends on the data set. But it's also scalable, right? Inception V1, the reason why they started naming it like V1 is because there are many other extensions of Inception, like Inception V2, V3, V4, Inception ResNet, etc. So it was a very scalable architecture. And it showed that instead of brute forcing the training or validation accuracy with just the sheer depth of the neural network, you can also have multi-scale filters. So filters of 1 by 1, 3 by 3, 5 by 5 sizes operating in parallel and having, as a result, lesser number of parameters and not like insane depth, and still get better performance. So it was, although this looks like a bit complex model, like to me, to my eyes, when I look at it immediately, it looks a bit more complex than the simple 3 by 3 convolution filters used in VGG. In reality, this is more simpler because the number of serial Inception modules that you need for getting depth, it's not that much compared to VGG. So total number of parameters were much lesser. So this is what Inception accomplished. So now let's have a proper look at how does the GoogleNet Inception V1 looks overall. So overall, this one single unit is what we discussed so far. From the previous layer, there is 1 by 1 convolution, 1 by 1 convolution, 3 by 3 max pooling. Then here there is 1 by 1 convolution. So look at the operations happening in parallel. So from the previous layer, you are performing these operations in parallel, and then we are concatenating everything into one single layer. And the total number of channels here after concatenation will be sum of the total number of channels in this plus this plus this plus this, right? So this is one Inception module or one Inception cell. And you can see this repeating over and over and over. So the total number of parameters over here in this entire architecture is what you saw earlier, around 6.8 million, which is pretty good. And here in this image, the color coding convention is such that blue is for convolution. So all these are convolution layers. Red is for max pooling. Green is for concatenating the channels. So whenever you see this green, you assume that the previous, however number of channels the previous layer had, the number of channels are getting added in this particular layer. And then you have fully connected layers, you have normalization, and of course you have softmax as activation for getting the final probability output. So this softmax will convert the previous fully connected layer into a probability distribution. This one, softmax. So this was the architecture. I'm sure the researchers who proposed this architecture would have gone through many iterations, and I'm sure they're also super smart. But it's almost amazing to me that humans could come up with architectures like this with certain kind of philosophy, and they managed to make it work better than what was proposed earlier. So each time you see a new CNN architecture, you feel like, oh wow, this is the final amazing thing. You can't become better than this. Then somebody will come up with a new architecture which is even better. So it's amazing to me that there is no end to the human creativity when people are developing solutions for different types of problems. So this is a perfect example of that. So now with that, let's get into the coding part, where we will implement the pre-trained Inception V1 for our 5 flowers dataset. So first I will show you just the parts of the code which are relevant to you, where I have made changes compared to the previous version, because there are only very few lines of changes. I'll show you that first, and then I'll show you the entire code. And because the execution of the code takes some time, I will show you the results directly, so that, and then of course you will get access to the code and you can run it yourself to get the same results. As we always do, we are storing the results of our code execution into weights and biases, so that it's easy to make plots, easy to create reports, etc. So let me show you the weights and biases final output so that you can see what exactly it is. I have already made an entire detailed lecture on this, which you might have gone through, but if you haven't gone through it, just understand that weights and biases, it's a platform, it's a website which allows you to directly connect with Google Colab, so that all the results of your execution is logged iteration after iteration, so that making plots and deriving insights is very easy. So this is the weights and biases platform, and this is the final results that I have. I'll get to that in a moment. But basically, the changes are in these weights and biases initialization parameters. So I just renamed the project as Inception Flowers. Previously, it was called VGG Flowers. So I just renamed it so that this is stored as a different project. And then this architecture name is insignificant because we are not using this anywhere. But just for the sake of reference, I just added the architecture name as Inception V1. You can completely delete this line of code also. It does not make any change. Then the major changes in the place where we define the pre-trained weights. So I have in the place where we import the pre-trained architecture. So there is one extra line from torchvision.model. So we are using this from PyTorch. We are importing GoogleNet weights. And then we say model equal to models.googlenet. So we are using GoogleNet architecture from this models package. And then we say the weights that we use are these GoogleNet weights. The default GoogleNet weights. So we are using a pre-trained architecture. So that we have already also mentioned here saying pre-trained equal to true. But this also is again inconsequential because anyway, we are directly using the pre-trained weight. So it doesn't matter whether you mention false or true here. We are not using this directly, but this is just for reference so that whoever is looking at the code, they can immediately see by looking at the config parameters that this is a pre-trained architecture. It's Inception V1, epochs are 50, batch size is 16, etc. Then the default input size of images for Inception V1 is 299, but we are using 224 because 224 is our original image dimension, 224 by 224 by 3. Then we say we replace the final layer with the 5 node layers because we want to perform 5 class classification. So we add a fully connected layer where you have 5 nodes. So this will be the very last layer. Then we have a code which we have been using so far. There is a minor change in the syntax. So that's why I highlighted this block of code in yellow. Basically, we say that we freeze all the layers, but except final classification layer. So except the final classification layer, we freeze everything, meaning in the back propagation, only the final classification layer nodes, the weights of those nodes are going to change. The rest of the architecture is intact. Meaning the weights that we import from the pre-trained GoogleNet are used as such. Then that's it. Basically, that's the only place where we have some changes. I'm going to show you the code right now, but let me show you the results first so that you will have more appreciation. So basically, we have validation accuracy once again higher than training accuracy, just like what we got for VGG. Validation accuracy is reaching somewhere close to 87-88%. Training accuracy is like 86%. So this is much better than VGG. In fact, VGG had 75% as training, 85 as validation. Here we have 85 plus for training and maybe close to 90 for validation. It shows that we are still underfitting because training can become even better. Validation can also become slightly better, right? So this shows that how powerful the pre-trained weights of this neural network is. Now let me show you the full code. This is the Google Colab code file. I'll share this with you. Everything else is same as what we have been doing so far in this course, except I have defined the architecture name, the project name I have renamed. I showed you this. And there is a place where when you run this block of code, they will ask you the weights and biases API. You can get that from the weights and biases. Go to this quick start. Click this from your dashboard. Go to quick start. Here in weights and biases models, you will get the API from here. You can copy and paste it. Then in the data pre-processing part, in the VGG, we had added some flipping, cropping to 224 by 224, etc. Here, it's not going to do anything because the default size itself is 224 by 224. And this random flipping and normalization is a standard procedure in the pre-processing of data. And of course, the data set I have stored in my Google Drive. So I'm connecting my Google code with Google Drive and I'm getting this data set, the images from my Google Drive. And I will share the Google Drive link with you, which I have already done in the previous lectures. So if you have it already, feel free to use the same link. Nothing changes in the code. But if not, if you are looking at this for the first time, then just copy the Google Drive folder from the link which you get, and then appropriately provide this URL. Then in the pre-trained model, we are importing GoogleNet weights and we are importing GoogleNet model. And in the parameter, we are saying the weights are same as the default weights from the GoogleNet pre-trained weights. And that's it. Then the rest of the code is pretty much the same standard things. You run once in around 10 epochs, you print the batch accuracy, and then every epoch you print the total training accuracy and validation accuracy and loss. So the reason why here also I decided to run 450 epochs instead of 10 epochs is because initially training accuracy was 70, validation was 85. So, and here actually I could have stopped at 10 epochs, but I was thinking anyways, VGG was performing better with 50 epochs. So let me try that. So here you see there is no overfitting or underfitting. It's almost training and validation accuracy is very similar. By 50th epoch, let me show you the exact numbers. So this took me around some time to run, like 1 hour or something. 1 hour, like 2 or 1.5 hours, something like that. But training accuracy is 86%, validation is 87. In some epochs, I think the training validation accuracy had even touched 90. So this was 88, 87. Yeah, close to 88, 90. So it's pretty consistent. But I'm pretty sure that if we run this for 200 epochs, maybe this will climb up even more to beyond 90, maybe even as close to LXNet, right? So, but the thing is, LXNet was still faster than this in terms of execution. So yes, VGG was amazing. It took a lot of time to execute. Number of parameters were huge. Inception V1 is also amazing, but for the specific data set that we are using, still LXNet is the best. But I'm pretty sure for other data sets, perhaps VGG or Inception V1 works better. So just as a conclusion from our results, what we did was we only trained the classification layer, the 5 node layer, right? Every other layers were frozen. then the pre-trained convolutional layers are already good at recognizing natural objects or natural images. Flowers are natural images because the original ImageNet data set by Google from this website. So this was part of the ImageNet competition, right? So they have a lot of manually labeled millions of images, mostly natural images. So these weights are already suited to identify natural objects. So maybe that's why validation accuracy is very good right from the first epoch, right? But classifier may not have, in the training set, you have a set of images, but the weights in the final layer are kind of random. So the classifier has to adapt a little bit for making predictions in the training set. So maybe that's why training data set accuracy is not high in the beginning. Validation is higher already from the start, but it's good. Like, we can train for more number of epochs and make this neural network even better. So it's a good thing, unlike overfitting. But the conclusion here is that it does not necessarily mean that all this depth and width is always better for all sorts of data set. That is not true, because AlexNet had a simpler architecture. AlexNet was, so far in our 5 flowers dataset, AlexNet is working the best. VGG had a bit more simpler architecture, but more depth. VGG was not working the best for AlexNet for 5 flowers. Inception V1 or GoogleNet is better than VGG, but worse than, slightly less good compared to AlexNet, right? So I'm pretty sure this depends on the data set, but at least for the context that we are in, we can conclude that these are all good models because overfitting is not happening. You are getting closer and closer to 90% accuracy, and with good hyperparameter tuning, perhaps you can reach closer to 95-100%, right? So that is the task of a machine learning engineer. But for our purpose of academic understanding of computer vision models, I think we have done a good job. But before we conclude this lecture, let me take a moment, as I usually do, to congratulate you for finishing another wonderful step. It's a small but significant step in your CV journey. We have finished lecture 0 plus 10 other lectures. So almost 11 lectures are done. So I would say around 33% of the course is done. So if you have come this far in this lecture series, I really congratulate you. You have done a very difficult job compared to most of the people. So you should feel proud of yourself. And more importantly, you should come back to the course to finish the rest of the lectures in this course. So I'll see you again in the next lecture. Please take care until then. Bye.